Chapter 11, Solving Quadratic Equations, some Cubics, and Long Division. Okay, so we're mostly doing algebra this week. We'll begin by looking at quadratic equations, answering what they are, what are their zeros, otherwise called roots, and how do we find those roots. Then we'll consider more general polynomials, as in cubics, and possibly even some quartics, and then using long division to find their factors and hence their roots. Alright, a quadratic equation is an equation of the form y equals ax squared plus bx plus c, where a, b, and c are elements of some particular set. Okay, however, usually, at least for this, at least for this course, A, B, and C are real numbers. And we need A to not be equal to 0, because if it were 0, then we would just have a line. Alright? So A is non-zero. Does usually have two L's? Okay, I don't know right now. So we can write this in the form y equals f of x, where f is a function, so you input x and you get out a number. F of x is a quadratic function. Notice the highest exponent in that quadratic is a 2. So we have a 2 there. That's the highest exponent. So we say that f of x has degree 2, and that makes it a quadratic. Whereas if the highest exponent were 3, we would say that the polynomial has degree 3, and we would call it a cubic. If it has degree 4, we would call it a quartic. If it has degree 5, then we would call it a quintic, and so on. So let's have a look at some graphs of quadratics. So on the left we have y equals 2x squared plus x minus 3, and you'll notice it has 2 points of intersection with the x-axis. One at, I don't know, that looks like minus 1.5 and plus 1. Okay, so those correspond to roots of that quadratic, otherwise called zeros, because they make f of x equal to 0. Now, it's pointing up like a bowl or a smiley face, if you like, so you can decide which way that should be based on the sign of that leading coefficient, as in the number next to the x of the highest exponent. Since it's positive here, it's like a smiley face, but you'll notice this one here is more like a frown face. And so we can decide that that's the way it should be plotted because it has a minus number next to x squared. So its leading coefficient is negative, meaning that it will be plotted this way. Alright, so this third one will have a leading coefficient that's positive. In fact, we have y equals x squared, so 1 is the coefficient of x squared. 1 is positive, and so it's plotted this way. Alright, this second one, y equals minus x squared plus 2, has 2 roots. This and this, right? And so looking at this equation, we could factorize that as minus in brackets x plus root 2 times x minus root 2. So this is the square root of 2, and this over here is minus the square root of 2. Those are our 2 roots. Whereas this one here has one distinct root, but since I can write y equals x squared as y equals x minus 0 times x minus 0, I could call that 2 roots where 0 is a repeated root. Now the fundamental theorem of algebra says that the number of roots, provided we're willing to accept repeated roots and complex numbers, as in not real numbers, the number of roots is equal to the degree. So our quadratics will always have 2 roots, provided we're willing to accept duplicates as 2, and provided we're willing to accept non-real numbers. Then we get 2. But if you want to look at that another way, we have up to 2 distinct roots. So we could have no real roots, we could have 1 distinct real root, or we could have 2 distinct real roots. Okay, let's have a look at example 11.1, but I think I'm going to redo this so we can talk about it along the way. Find 2 numbers whose sum is 1 and product is minus 12. Okay, let's call them x and that says z, so we'll stick with x and z. Okay, so if they are x and z, then the sum is 1, right? So that's the first part of that statement, and the product is minus 12. So x times z is minus 12. Okay, now we can treat this as a simultaneous system of equations, but notice the first equation is linear, the second equation is nonlinear because I'm multiplying 2 of the letters. So as a system, this is a nonlinear system of equations. However, it's easy enough to solve, whereas most nonlinear systems of equation are not that easy to solve by hand. Okay, so the way we might want to solve this is to solve the first one for z. So z is equal to 1 minus x, and then substitute this into the second equation so that we have x times 1 minus x, which is our z, equals minus 12. Alright, now this, when you expand it, you'll get a quadratic equation. So on the left we have x minus x squared, and on the right we have minus 12. So if we add the additive inverse of this left-hand side to both sides, we'll have a leading coefficient that's positive, and that's nice. So we'll get x squared minus x minus 12 is equal to 0. And so now we have a choice. We can factorize this, or we can use the quadratic formula. So since we haven't fully discussed the quadratic formula, let's factorize this. Alright, so now the divisor pairs of 12 are 1 and 12. We have 2 and 6, and we have 3 and 4. Now this is negative, right? So I want one of these to be plus and the other to be minus. And so that means I need their difference to be minus 1. So I have to choose this one because that's the only one that has a difference equal to minus 1. So I'll write x with brackets, and then I'll put in a 3 and a 4, and next we want to decide the signs. Okay, so one has to be plus, the other minus. They have to add together to give minus 1, so that means I want the larger one to have a minus sign in front, and the smaller one to have a plus sign in front. Okay, so this expands to give this. So this is these are the factors of that quadratic polynomial, and so we can clearly see what the zeros are. They are the x that give us 0 when we sub them in, and so that would be minus 3 for this and 4 for this. But we can do this in another way, because if we have the product of 2 numbers equal to 0, then at least one of them has to be 0. So x plus 3 equals 0, or x minus 4 equals 0. So the left one gives us x is minus 3, and the right one gives us x is 4. So this is a way to find the roots, or the zeros, of our quadratic polynomial. Alright, so now we found two numbers that add to give 1 and have a product of minus 12. So we've completed that example. So let's go ahead and have a look at example 11.2. Factorize the quadratic polynomial and hence find the zeros of f of x. Okay, likewise I'm going to do this again on paper. Alright, so first factorize. Okay, so we look at the divisors of 21. We have 1 and 21. We have 3 and 7. Alright, so there are no other divisors up to swapping around. And we don't need to swap around when we list the divisors. Alright, so the question is, do any of these have a difference to give us 4? And yes, it's the second one. Alright, so we can write then that f of x is equal to x brackets x. Now we've got to put in a 3 and a 7 and decide the signs that go in front of these. So one is plus, the other is minus, because that product is minus 21, but they add together to give plus 4, so I want the smaller one to have the minus sign on it. Okay, so I have my two factors. Now the zeros are what make this 0 in both cases. So let's say alpha 1 is 3 and alpha 2 is minus 7. These are the zeros, or the roots, of that function. Okay, let's move on to the next page. Where we have a theorem. If a, b, and c are real numbers with a non-zero, so that it's actually quadratic and not linear, satisfying f of x is a x squared plus bx plus c equals 0, then we have the quadratic formula, which you should have already memorized, hopefully. If not, please memorize it, because it's useful and important. Alright, but let's have a look at some special cases. If a is positive, then the quadratic curve has a minimum value at the point minus b on 2a, comma, minus in brackets, so brackets around that if you like to avoid confusion with the minus sign, b squared minus 4ac over 4a. Alright, now there's one way to do that via calculus, right? But if you haven't done a calculus course, then there's also an algebraic way to do this, or to establish that this is the minimum value, or the minimal value is attained here at this point. You can do it algebraically by completing the square. If a is negative, then the quadratic curve has a maximum value at that very same point. Further, since the degree of the quadratic is 2, we have two solutions. If b squared minus 4ac is negative, so notice that's what we call the discriminant, so it's inside the square root there. So if that's negative, then notice we will not have a real solution. So the roots are not real numbers in that case. So if the discriminant is 0, well, put in 0 there, so we have minus b over 2a then. That's a repeated root. So in other words, f of x would be equal to x plus b over 2a times x plus b over 2a. Right, so it would be a perfect square. And so the roots are minus b over 2a and minus b over 2a. So we say that's a repeated root. But there's one distinct root. If b squared minus 4ac is positive, then the two roots, this one and this one are both real numbers, and that's because the square root of that discriminant will be a real number. Therefore, minus b plus or minus that real number, the square root of the discriminant, all over 2a is a real number. Right, and notice this is because we've assumed that a, b, and c are real numbers. Alright, so that covers the three cases. So the fundamental theorem of algebra says we always have two complex roots, but in the first case we have no real roots, so 0 real roots. In the second case we have 1 distinct real roots, but 2 if we count this as repeated. And in the third case we have 2 distinct real roots. They're distinct because this one has a plus and this one has a minus, and that square root is non-zero, so they are in fact different. Okay, so to verify this part of the claim, we complete the square, and we'll do completing the square rather than calculus because this is an algebra course mostly. Alright, so I want to rewrite this by hand here, even though it's already typed. So we have our equation. Hang on, I need the focus to come back. Come on, focus. There you go, thank you. Alright, so multiply by 4a, and the reason we do that is because it ensures that the leading coefficient becomes a square. So we will have 4a squared x squared plus 4abx plus 4ac is equal to 0 times 4a, which is 0. Okay, now if we just focus on this part, this is almost a perfect square. The only thing we're missing in having what's in the brackets being a perfect square is we need a plus b squared. So let's impose that, but if we impose it inside the brackets, we have to compensate for what we've done to make the equation still true. So we have 4a squared x squared plus 4abx plus b squared. I'll leave the bracket there, and then outside the bracket I'll put minus b squared and then plus 4ac, which is what we have from there. Okay, so you see b squared minus b squared is 0, so there's nothing different here, right? These are the same equation. However, what is in the bracket is now a perfect square. It is 2ax plus b all squared, right? And if you expand that square, you'll see that you get exactly this. Okay, and then let's write this as minus in brackets b squared minus 4ac. So you can already see it has some things in common with that formula, right? So we're on the right track. Okay, so what we want to do is solve for this, right, so that we can solve for x. So we'll take this over to the right hand side and say 2ax plus b squared is b squared minus 4ac. And now we can take square roots, alright, so that 2ax plus b is equal to plus or minus, because we're solving for 2ax plus b, so we get this now. Right, now we're nearly done. We just have to subtract b from both sides and then divide by 2a. Okay, so subtracting b from both sides, and then since a is not equal to 0, there's no problem in dividing by a, so we can divide by 2a and get x is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. And that's our quadratic formula. And we achieve this by completing the square. All right, let's move on to the next page. So let's have a look at example 11.3 now. Find the zeros of the following quadratic equation. Now, possibly annoyingly, it has a decimal number in there, so you can, if you want, multiply throughout by 2 and just have integers. So let's do that. So multiplying by 2, we have 2x squared plus 5x plus 2 is 0. Alternatively, you could set a as 1, b is 2.5, and c is 1, and sub that into your quadratic formula. Now let me have a peek at what's done here. Yes, the formula is used. Okay. So what if I wanted to do this instead by completing the square? Okay, so I can see that the formula is done here, so why don't I do this instead by completing the square? So if I were to do this via completing the square, I would be multiplying by 2, and the reason is because that would make this a perfect square. So that would give 4x squared plus 10x plus 4 is 0. Okay, so now this part is almost like a perfect square. I need 2x plus something all squared. Now what is that something I need? Well, when I square this, I get a 2 times something times 2 because I'm squaring, so that generates 2 of them. So 4 times something gives me 10, so 10 over 4, which is 5 over 2. Alright, now check what happens when we expand this. We get 4x squared plus the product of these two is 5x, but there are 2 of them when we expand, so that gives us 10x. But now I've generated the square of this, so I have to subtract its square to make this true. Okay, so we have this. So it might have been a little bit more convenient if I multiplied by, instead of 2, if I multiplied by 8. Right, so I could have done that. Alright, now to complete this square, I mean it is completed, but to solve for x, I would want to take this over to the right hand side. But first, what is this? This is 16 over 4. Okay, so we have then 2x plus 5 over 2 all squared is 25 minus 16 all over 4. So I'm taking it over and then I'm writing this over 4, which is 16 over 4. Now 25 minus 16 is 9. So that's 9 over 4. So now taking square roots should be fairly easy. So 2x plus 5 over 2 equals plus or minus the square root of this, but that's 3 over 2. Okay, next we want to take this over. So 2x equals minus 5 over 2 plus or minus 3. Now I've written that over the single denominator 2 because we can there. It's common. And then we divide by 2 and we have x is equal to minus 5 plus or minus 3 all over 4. Okay, let's see what the two answers are. So if we're looking at plus first, then we have 3 minus 5 is minus 2 over 4. So x is minus a half. Or if we subtract, then we have minus 8 over 4. So that's minus 2. Okay, now let's see. Does that agree with what we have there? Yes. All right, so let's get the focus back. Yes, there we go. Okay, so in this version, you're just subbing in the a, which is 2, the b, which is 5, and the c, which is 2, into the quadratic formula, and you simplify. Right? Which is pretty easy. Alternatively, like we said before, or we could put x is 1 or sorry, A is 1, B is 2.5, and C is 1. Just from there, and you would get the same result. Okay, next up, example 11.4. Find the zeros or roots of the following equation. Okay, here, hang on. Here we've got a minus 6.7. Now you could multiply throughout by 10, right? But this time I'll just keep it as is. Let's keep A is 1, B is minus 2, and C is minus 6.7. So our quadratic formula says x is equal to negative b, which is plus 2, plus or minus the square root of b squared, minus 2 squared is 4, minus 4 times a, but a is 1, times c. Now keep a bracket around this to be careful with that minus sign. So we have minus 4ac there. Okay, now this is all over 2a. A is 1, so that's all over 2. Okay, so we need to simplify this. There are two minuses there, so that makes a plus. So we can write 2 plus or minus the square root of 4 plus, now 4 times 6.7. Let's see, what is twice 6.7? It's 13.4, and then twice 13.4 is 26.8. Okay, now this becomes inside the square root 30.8. So 2 plus or minus the square root of 30.8 all over 2. Now I don't know the square root of 30.8 off the top of my head, but it looks like it's 5.5497. Alright, so I'll keep looking at this now. Right, so we take 2 plus 5.5497 all over 2, which is 7.5497 divided by 2, and that gives us 3.77489, and so on. Or in the minus case, 2 minus 5.5497 is, I don't know, let's see, minus 3.5497, and if you divide that by 2, you've got minus 1.774 8, and so on. Okay, great. So we have solved it. Now let's go and have a look at the geometric meaning of the roots of quadratics. Well, they correspond to intersections with the x-axis when you plot the curve. So remember what the discriminant is b squared minus 4ac, and that tells you the number of distinct roots that you have. So if the discriminant is positive, then you have two real roots. But conversely, if you have two real roots, then you have a positive discriminant. And so we say that delta is positive if and only if f of x equals 0 has two real roots. That coincides with the curve crossing the x-axis at two real valued points. Okay, the next case, if delta is 0, then we have one unique real root, or equivalently two repeated real roots. But conversely, if f of x is 0 has one real root, then we have a zero discriminant. So we say if and only if. And the last case is if delta is negative, then we have no real roots. They're both, in fact, non-real complex numbers. So that coincides with the curve having no intersections with the x-axis. You wouldn't be able to see those intersections because they're not real. Alright, so here's an example of that in figure 31, or 32. We also have it in 31. Okay, so here's figure 32. Y equals x squared plus 2. Now you can see if you try to solve this equals 0, you would have So x squared plus 2 equals 0. If we try to solve this for real numbers, we've got x squared is equal to minus 2. Alright, that's a contradiction, assuming that x is real, because squares of real numbers are greater or equal to 0, and this clearly is not. But now if we take the square root, so we have x equals plus or minus the square root of minus 2, which we can write as the square root of 2 times the square root of minus 1. Okay, now this number is normally referred to as the letter I for that purely imaginary number, the square root of minus 1. So we could say that this is plus or minus root 2I. Right, but this number is complex and not real. So x does not belong to the real numbers. Okay, I'll just add at this point that complex numbers that are not real, those are just words, right? They're every bit as real as, or as tangible, I should say. They're every bit as tangible as real numbers. And in fact, they get used in applied mathematics. Take, for example, an equation that has derivatives in it. Hey, I might even give you an example here, because I can probably think of one off the top of my head. If we just consider the differential equation y double dash of x being the second derivative plus y dash of x plus y of x equals 0. So there's this very simple differential equation, and these are commonly used in engineering. Okay, so this would have a characteristic equation that has complex roots, and so there's an intermediate step in solving this whereby you need to present certain parts of it in terms of non-real numbers. But then in the end, since that's intermediate, you come back to find that your solution is real and even tangible. Right? So you would get a periodic solution, something involving sine and cos. But that's an aside or a digression. So let's get back to this. Polynomials of degree greater than 2. Okay, so a univariate polynomial, so that means one variable, is a finite sum of constants times non-negative integer powers of a variable, say x. So in other words, like this, right? So finite sum, so this stops with a finite non-negative integer n in order for this to be a polynomial. And we have coefficients. We would have n plus 1 coefficients, right? These make n coefficients, but then we have this one as well, makes n plus 1 coefficients of a degree n polynomial. All right, so this is an example of a univariate polynomial. The degree of the polynomial in this equation is n, because that is the highest exponent. Okay, notice we can conveniently represent this in a summation notation also, right? So that this is just shorthand for this. But what this says is sub in j is 0 here. We get this. And then add to that, that's what the sigma means, it's a Greek S. Add to that what happens when we sub in j is 1. Okay, we get a1, x to the 1, that's that one. Then add to that what happens when we sub in j is 2. We have a subscript 2, x to the power of 2, that's that one. And then dot 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 and so on. And then it says stop when j is equal to n. That's where we stopped. Okay, sometimes that's useful theoretically. Like if you want to prove certain things about polynomials, then that's a useful way to express them. Now, as a vector, we can write this polynomial like this, right? There is a one-to-one correspondence between this polynomial and this vector right here. And that correspondence has preserve certain algebraic properties, like the fact that you can move brackets around when you add 3 of them together, and several more. Alright, let's have a look at some examples of polynomials. So 3x squared minus 7 is a polynomial of degree 2. Alright, so there's the degree, it's 2, that's the highest exponent. Our coefficients are 3 and minus 7. Minus x to the 15th plus 7x to the 4th plus 5x squared minus 1 is a polynomial of degree 15. 15 is the highest exponent. Minus 3 is a polynomial of degree 0. Okay, all of the x's that are in this minus 3 are of power 0. So x to the power of 0 is 1. Okay, some examples of univariate polynomials are, hang on, that can't be right. So multivariate polynomials. This is a multivariate polynomial. And why? Because the 2 letters, well, there are 2 letters, right? So it's bivariate, 2 variables, which makes it multivariable. Oh, I see, non. I didn't read the word non. Okay. So I can get rid of this. That's okay. Some non-examples of univariate polynomials. So these are not univariate polynomials. And the reason why this is multivariate, this one is not a univariate polynomial because the powers need to be non-negative to be called a polynomial. Similarly, 4 over x squared minus 2 is not a polynomial because we don't have this expressed, or it's not possible to express this as a finite sum of real numbers times powers of x, where the powers are non-negative. All right. So incidentally, you can write this via Taylor series as an infinite sum or an infinite degree polynomial, but remember that's not a polynomial. And the reason why that's not a polynomial is because not finite degree. Okay, great. So let's now move on to polynomial long division. So here's an example, and I reckon this probably comes from, oh, I don't know where I got this. Did I get this out of Lauren's video? I'm not sure. So here's an example of long division with numbers, all right? So I won't go over that. I'll just go straight to the long division with polynomials. Okay, and what I'm going to do is I'll redo this here in the margin just to show you how it works, because it's not so helpful to see it already done. It's more useful to see the process of doing it. All right, so this says calculate this using polynomial long division. Okay, now this is probably the hardest example because I can see it's got a non-zero remainder. So let's set it up. So we take the denominator, we put it to the left of our numerator with this little division sign, just like you did in grade school. And we write 6x squared plus 7x plus 8. And now we ask ourselves, okay, what do I need to put here so that this 2x times this equals this? And that's the question, what is 6x squared divided by 2x? Okay, well it's 3x. So we write 3x there. And our next step, once we've done that, in other words 6x squared divided by 2x is 3x, we write it up here and then we expand 3x times 2x minus 4. All right, so where can I write this? I'll just tell you on the side. Okay, so I'm multiplying 3x times 2x, that is 6x squared. That's exactly what I expect to get because that's how I got it. Remember, I got it by a division, so the product should give me the original 6x squared. And then I take 3x and multiply by 4 and get 12x. Okay, I draw a line. But what this is equal to 3x outside of, I don't have much space to write this, 2x plus 4. It's probably not visible to you, but that's 2x plus 4 and 3x. Okay, so next thing I do is I take a difference. Now you'll notice here we've got minus signs in, so you can do that too, but I'll just take a difference and write down the difference here. So I'll do it slightly different than what's done here. So the difference is, so this difference is 0. This difference here is 7x minus 12x is minus 5x. And then I carry this down, right? Or 8 minus 0 is plus 8. And now I repeat that process. I ask the question, what do I need to multiply 2x by in order to get minus 5x? In other words, what is minus 5x over 2x? Well, it's minus 5 over 2. Okay, and so now we take this, we multiply by the whole thing over here, and so we get minus 5x, and then minus 5 over 2 times 4 is minus 5 times 2 is minus 10. Okay, I draw a line, and now I'm going to take a difference. All right, so this minus this, which would be minus 5x plus 5x is 0. That's 8. Minus 10 is 8 plus 10 is 18. All right, so next we ask, okay, what is 18 divided by 2x? Well, that's not an integer, right? So we stop here and we call this the remainder. So that's our remainder. Okay, now how do we express that? Well, we express it like this. We have that this quotient over here is 3x minus 5 over 2. That's what we got there. And then plus the remainder over the denominator. So plus 18 over 2x plus 4. Okay, and we can now take this and rearrange it to say that multiplying both sides by 2x plus 4, so we have 2x plus 4 times 3x minus 5 on 2, and this 2x plus 4 would cancel, leaving the remainder 18 there, right? Now, if we want to relate this back to ordinary division, if x is equal to 10, then this right here is 30 minus 2.5, 27.5 plus 0.75, which is 28.25. And let me see, is that what we had here? Yes, and so what that says is that you can do this by doing polynomial long division, because you could say that that's 2 times 10 plus 4 divided by 6 times 10 squared plus 7 by 10 plus 8, and we got 2 times 10 to the 1 plus 8, and then plus another remainder, right? plus something else. All right, so that's the similarity here. You can do this problem by polynomial long division if you want to. Okay, so let's have a look at theorem 10. Let f of x be a polynomial with real coefficients, then there exists an alpha satisfying f of alpha equals 0 if and only if there exists a constant k that's a real number such that k times x minus alpha is a factor of f of x. All right, that's a pretty important theorem, because it says that whenever we happen to be able to find a zero or a root of our polynomial, that tells us immediately what a factor is of the polynomial, and by attrition we can more easily factorize, say, a cubic or a quartic if we happen to know what one of the roots are. Okay, so let's have a look at this example here. All right, and I'll sort of redo this by hand here. So just looking at this, the question is, can we find a root of this just by guessing, right? Some small numbers. Okay, so this says f of 1, subbing in that, we have 1 cubed plus 2 times 1 squared minus 1 minus 2. That gives us 0. So we know that by the theorem, right, and since we have a leading coefficient of 1, we must have x minus 1 is a factor of that cubic, x cubed plus 2x squared minus x minus 2. Okay, and so given that, we can set up a long division where we put x minus 1, x cubed plus 2x squared minus x minus 2, right? Because this says if x minus 1 is a factor of this f of x, then x cubed minus or plus 2x minus x minus 2 divided by x minus 1 is a polynomial. Okay, so let's write that. X cubed plus 2x minus x minus 2 over x minus 1 is a, we don't even know what degree it is, it's quadratic. It's a quadratic polynomial. Right, so that's why we set up a long division. We want to find what that quadratic polynomial is so we can find the other factors and thereby find the other roots. Okay, so our long division starts by setting this up. We look at this leading term, x cubed, we divide it by x and we get x squared. So we write that x squared here, and then we take x squared, multiply it by that whole x minus 1, write that below, and we get x squared times x is x cubed, and then we have minus x squared. Draw a line and take a difference of this minus this. Okay, so then we have 0 for that. We have 2x squared minus x squared is 3x squared. We bring this down because that's minus x minus 2, take 0, which just gives this. And then we repeat the process. Okay, so 3x squared divided by x is 3x. We take this 3x, we multiply by x minus 1, and we have 3x squared minus 3x. Draw a line and take a difference. We have 0 for that. Minus x minus 3x is 3x minus x, which is 2x. Bring down the minus 2. Okay, repeat. 2x divided by x is 2. So we put plus 2 there, and then we take that 2 and we multiply it by the whole x minus 1, and we have 2x minus 2. We take a difference. This time we have a remainder of 0. That's great because that says that this polynomial is in fact divisible by this one because the result is a polynomial with a 0 remainder. Okay, so let's reiterate what we have done. We have shown then that x minus 1 multiplied by x squared plus 3x plus 2 is equal to that cubic Okay, so we have actually used that previous theorem, and I'll show you that again. There exists a real number alpha satisfying f of alpha equals 0 if and only if there's a constant k such that k times x minus alpha is a factor of f of x. So here we're showing it as a factor. X minus 1 is a factor, and that is because 1 is a root. Okay, so we use the fact that 1 is a root. We set up the factor x minus 1, and we did a long division to be able to write what we have here. So that makes the problem easier to find the roots, right? Find the roots. So all we have to do is find the other two roots, and they are the roots of that quadratic. Now we can factorize this by hand, this part, or we can use the quadratic formula if you're really stuck, but it's easy enough to factorize by hand because they happen to be integer roots. So the divisors of 2 are 1 and 2. So we'll write our 1 and 2. Now let's decide the sign. So this is positive, so these have to be of the same sign. But this is positive, so that means that they are both positive. Okay, so this is our factorized form of f of x. And now the roots satisfy f of x equals 0. That's why they're called zeros as well as roots. And so the roots are what makes these 0. X is 1, x is minus 1, or x is minus 2. All right, let's have a look at the geometry here. So that gives us 3 points where the y-coordinate is 0 of the equation y equals that cubic f of x, right? Because when we put in minus 2, we get 0 out of this, so we have a y-coordinate of 0. When we put in minus 1, we get 0 out of this, so we have a y-coordinate equal to 0, and likewise with 1. So that gives us these 3 points. Okay, but here is what the rest of the cubic looks like. It comes down from minus infinite. It's negative until we get to x is minus 2, and then it goes over the x-axis, comes back down to meet the x-axis again at x is minus 1. It goes negative again, turns around, and then it increases until we get to here, x is 1, and then f of x is positive again. Okay, example 11.7. I'm going to get some paper and redo this one. Find the zeros of the polynomial, this one right here. It's got a leading coefficient of 2. Alright, so just doing some guessing, you might sub in 1, you see that you don't get 0. You sub in minus 1, you see that you don't get 0. You sub in 2, you see that you don't get 0. Then you sub in minus 2, and in that case you get 0. Right? So f of 1 equals 2 times 1 cubed minus 1 squared minus 13 times 1 minus 6, and let's simplify that. That's 2 minus 1 minus 13 minus 6. Well, that's 2 minus 20, I think, which is minus 18. Okay, that's not equal to 0, so 1 is not a 0 of that cubic polynomial. All right, dot, dot, dot. F of 2 does give 0, and f of 3 does give 0. So that tells us that x plus 2 and x minus 3 are two factors of f of x. Okay, now setting out the long division, so we could choose any of these to do a long division with, because we're meant to get a polynomial as this cubic divided by x minus 3, but we could also divide it by x plus 2 and we would get a polynomial, in particular a quadratic polynomial. Okay, so here's another example of such a division, and you get a 0 remainder as expected because this is a factor. So this divided by x minus 3 should be a polynomial, and we see it is because we have a 0 remainder. Alright, but you could also do, I'll just take this opportunity to multiply those two out just to show you another example. So x plus 2 multiplied by x minus 3, just expanding this gives us x squared plus 2x minus 3x minus 6. So we have x squared minus x minus 6. Okay, so let's deal with that one as well, just to show you a different kind of example. I can put a quadratic out the front here. And then inside we'll put that cubic. So what I expect to get when I do this long division is I expect to get a linear factor, which is the missing factor there. So let's go ahead and do this. I want to better focus here first. Okay, there we go. Alright, so 2x cubed divided by x squared is just 2x. Okay, then I take my 2x, I multiply by this, and I have 2x cubed minus 2x squared minus 12x. I draw a line and I take a difference. I have 0 there, minus x squared minus 2x squared is 2x squared minus x squared, which is x squared. Okay, minus 13x minus 12x is minus 13x plus 12x, which gives minus x, and then we bring down our minus 6. Okay, now we repeat. What is x squared divided by x squared? It's 1. Okay, then I take the 1, I multiply it by this. Well, look, it'll be the same, won't it? So x squared minus x minus 6, take a difference, get 0. That's what we expect, a 0 remainder. Because this cubic is divisible by the product of x plus 2 and x minus 3 by that theorem before. So what we've learned then is that f of x is equal to x plus 2 times x minus 3 times 2x plus 1. Okay, now this is an alternative approach where you just take one of them and divide and you get this, but then you have to factorize that. So what's happened next there in the printed example is we've taken that and used the quadratic formula to solve that. But you can see from this version it's really easy to see what the roots are. So the roots just from this are x is minus 2, x is 3, or when this is 0, x is minus 1/2. Which is what we get there. Okay, great. Let's move on. to example 11.8. Find the zeros of the polynomial x cubed plus 7x squared plus 11x plus 5. So the divisors of 5 are plus or minus 1 and plus or minus 5. So choosing divisors would be a good choice here of the last one. F of 1 is 24, that's non-zero. F of minus 1 is 0, so that's good. F of minus 5 is 0. So what we've learned then is that x plus 1 and x plus 5 are factors of that cubic. Alright, so you could do this long division, or alternatively, now what is the product of these? X squared plus 6x plus 5. Okay, x cubed divided by x squared is x. X times this is x cubed plus 6x squared plus 5x. Take the difference, we get x squared plus 6x plus 5. That's the same as that. So I need a plus 1 here. And then we take the difference, get 0. And so that tells us that f of x is equal to x plus 1 times x plus 1, so there are two of them there, and times x plus 5. Okay, so we got this in another way. Now let's have a look at the plot. So in the plot it looks interesting because over here we've got our x is minus 5. Right here we have x is equal to minus 1. Okay, notice that's a repeated root. We have, according to the fundamental theorem of algebra, this cubic should have 3 complex roots where some of them might be repeated. So 1, 2, and 3. So roots are minus 1, and minus 5. Minus 1 is repeated. And that agrees with the degree. So the degree of f of x is equal to 3. In agreement with this. But there are 2 distinct roots. Okay, now this is a repeated root, so calculus will tell you that its turning point, or it's the point where it touches the x-axis, is actually a tangent. So the point minus 1, 0 is tangent, touching only at a single point, the x-axis right there. So tangent to y equals f of x, and it is the x-axis. That is the tangent line. And incidentally, the x-axis is the line y equals 0. Okay, let's move on to the next and last page for this video. Find the zeros of this polynomial. It's a cubic. Okay, so it's easy to see that f of 1 is no good because it gives us 6, which is non-zero, so x minus 1 is not a factor. The division, that division will leave a non-zero remainder. Well, just looking at this, I didn't find the factors at all, did I? Okay, so the roots are not real, it says. Yeah, you know what? I'm just a little bit skeptical of what I wrote earlier. So I'm going to get the computer out and I'm going to factorize this. Okay, so f of minus 1 is equal to 0. So instead what I should do is do the long division x plus 1 on the left of this. Okay, so let's do this long division because this should be a factor here. Now x cubed divided by x is x squared. X squared times x plus 1 is x cubed plus x squared. Take a difference, 0 there, minus 2x squared there, plus 2x plus 4. Okay, minus 2x squared divided by x is minus 2x. So we multiply this out and we have minus 2x squared minus 2x. Take a difference. That gives us 0 plus 4x plus 4. This is divisible by this, but specifically 4x divided by x is 4. And then 4 times x plus 1 is 4x plus 4. And so we have a 0 remainder. Okay, so that's great, because what that says is that x cubed minus x squared plus 2x plus 4 is equal to x plus 1 times x squared minus 2x plus 4. Okay, now the claim here is that the roots are complex. We do have one real root. Let's find the complex roots using the quadratic formula. So to find the other two roots, we want to solve x squared minus 2x plus 4 equal to 0. So we have x equals negative b, that's 2, plus or minus the square root of b squared minus 2 squared is 4, minus 4 times 1 times c is 4, all over 2a. Now this inside the square root is negative, it's minus 12, so 4 minus 16 is minus 12. So we have 2 plus or minus the square root of 12 all over 2. Now root 12 is the square root of 3 times 4. So this is 2 plus or minus 2 root 3 all over 2. 2 root minus 3, and that's actually minus 12, isn't it? So I'll put that minus in there. Okay, so both of these have a 2 in them. We can divide the 2, so that's 1 plus or minus the square root of 3 times I. So this is not a real number. It is a complex number. So given that, let's write our three factors given by the fundamental theorem of algebra. So f of x is equal to x plus 1, x minus 1 plus root 3i times x minus 1 minus root 3i. So our three roots are x is minus 1, x is 1 minus root 3i, x is 1 plus root 3i. Okay, three roots according to the fundamental theorem of algebra, because the degree of f of x is 3. Alright, that's all for today.